Hey guys, so in this video we are going to be talking about vectors. Now, as you probably know, vectors are extremely important in physics. And so this is just really a review video. Hopefully you're familiar with this. If not, go into Khan Academy. Um, they'll have a lot of vectors in their definitely in their pre-calc section. Um, but I don't want to spend too much time. I'm just going to cover the basics of, just the general basics. So first of all, we know that a vector has magnitude and direction, and it can be represented by sort of an arrow, where the magnitude, right, which is this distance, we'll represent that with absolute value signs. And this is the vector v, and it has this little vector hat on top of it to show that it is indeed a vector. Of course, examples of vectors can include things like displacement, right? Displacement is how much something moves. It moves a certain amount and in a certain direction, right? Or velocity, right? Velocity is speed, right? The magnitude and direction, what direction an object is moving, right? So there's a bunch of different examples of vectors. So now we look at the case of what if we have two vectors. I've got a vector right here. I've got a vector A. I'll redraw that. Got a vector A here. And I've got another vector B. Right? And so we can do a few things here. First, we can do A plus B, right? And so what we'd be doing with A plus B is we take A, switch this color, take A, and then we attach to the to the tip of A, we attach the tail of B. And this will get you vector A plus B. Right? So this is A plus B. Right? Similarly, A plus B is actually the same as B plus A. If we just think about it like this, here we've got B, and then to the tip of B we have A. Right? And if I actually drew this right, you would be able to see that this vector, which is B plus A, right, this is B and this is A, this vector B plus A has the same magnitude and direction as A plus B. It doesn't matter where they're placed on the sheet, because the vector is just defined by its magnitude and its direction. We can do a few things to, for example, this vector A, for example, we can have vector negative A. Where it is the same magnitude, but it's just flipped, right? Should be an A. Or we can multiply A by a constant, right? So let's say this is 2A. 2A, all we're doing is we're going to take A and double its length. This would be about the vector 2A, same direction. Then you can obviously see how we could do like B minus A. B minus A would just be B plus negative A, and so we just have it here, and then we'd have, negative A over here, and then this would be B minus A, which is the same as B plus negative A. So that's pretty basic. The important thing to realize here is that the greatest a sum of vectors can be, right? So is when they're in the same direction. So if this is I'm going to erase these vectors A and B. Hold on 1 second. I'm going to erase these vectors. Hopefully you had this down if you need it. So if this is vector A and this is vector B, these vectors are just going to add up, right? So we'd have, if we put them next to each other, this would be about A plus B. Right, so if they're in the same direction, in fact, the magnitude of A plus B is going to be the magnitude of A plus the magnitude of B. that is a special case. That is only when the vectors are in the same direction. In fact, the smallest it would be is if they're in the opposite direction. So if I have A here, and I have B here, right? This is just a different in B, so I'm going to erase that here. So if these are now my vectors, A plus B is going to be like that, right? Its magnitude is going to be smaller. And in general, if I have a vector like this and a vector like this, we know that based on just the triangle inequality, right? We know that this side, they don't have to be at a right angle, but the longest side of the triangle has to be less than or in a triangle, the longer side has to be less than the sum of the two sides, and that's what this sum is. So we know that A plus B, in general, the magnitude of the vector A plus B, it has to be less than or equal to the magnitude of A. I'm going to erase this, plus the magnitude of B. And you can just sort of see this geometrically. There's a rigorous mathematical proof, but I'm not going to go into that. So hopefully this makes sense. Now, the next thing I want to do, I'm going to erase this all. Hopefully you have it down if you need it. Is talk about vector components. So in 2 dimensions, we have our axes. We have, this is not straight, but it's fine. We have the x-axis and we have the y-axis. Now, we can see that a vector, this is my vector v, it has a component in the x direction and a component in the y direction. This is kind of hard to see because I am not the best artist on this computer, but you can see this vector is the sum of these two component vectors. So we'll call this Vx, and it's a vector, and Vy, which is a vector, right? And you can see that V is the sum of its x component and the sum that is the sum of its x component and the y component. So we could write that as V is equal to Vx plus Vy. Well, we also can see that if we have an angle theta here, didn't draw that well, but we can see that the magnitude of Vx, just based on trigonometry, is the magnitude of V, right? I'm just going to call it without a vector hat. It's going to be actually, I'll draw the magnitudes, the absolute values. But generally, if I don't draw the vector hat, that's just referring to the magnitude at that point. The magnitude of V, so Vx is magnitude of V times the cosine of theta. And similarly, Vy, the magnitude, is equal to V sine theta. You can confirm this with trigonometry. You'd see sine theta is opposite over hypotenuse, right? Cosine theta is adjacent over hypotenuse, so SOHCAHTOA. Right? The other thing we can see using Pythagorean theorem, because Vx and Vy are perpendicular, right? This is a right triangle. We can see that V, the magnitude of V squared, is equal to the magnitude of Vx squared plus the magnitude of Vy squared. Okay, perfect. I'm going to erase some of this. Keep this up. Cool. So now we can define what we call a unit vector. And a unit vector is defined by this property. So generally, at least for right now, we're going to represent unit vectors with a hat. And unit vectors follow this property that the magnitude of a unit vector is equal to 1, right? And so we have two main unit vectors that we're going to be using right now, and then I'll show you we're actually going to generalize it to 3 or more. We have the unit vectors I hat, right, which is 1 unit in the x direction, and j hat, which is 1 unit in the y direction, right? And so we can actually write a vector in this form, where we have, right, this vector v is, in this case, we have v is equal to vx. Vx is going to now, it's not the component vector, it's just the length of this component, or it would be negative if it's the other way, right? Vx times I hat, right? Which is, all it's saying is you're stretching the x unit vector, which has a magnitude of 1, you're just stretching it by whatever the magnitude is, or if it's negative, you're flipping it, right? Plus vy times j hat, right? And so this is just saying, right, this would be I hat, right? And here we'd have j hat, right, with a unit of, with the length of 1, and we're multiplying it by vx, and we're now multiplying j hat by vy, and we're adding them. This is the general form of a vector. With in unit vector form, this is also called a linear combination. This is a linear combination, and so we can represent a vector by the in terms of its components and unit vectors. We can add vectors additionally by adding their components. So this is going to take a minute, so I'm going to erase all this. I'll just show you a few cool operations we can do. A few cool operations that we can do with two vectors. So we've got vector A and vector B. And I'm hopefully gonna, this should be a little bit shorter, but well, we can break A up to in its components. We've got AX times I hat, and we can also do this with B. We've got gonna just move this over here. Sorry. Got, there we go. And I'm gonna label this over here as B. We've got bx times I hat. And then for our y component, our j component, we've got ay times j hat. And we have here, we have by times j hat. Now you can see actually by is going to be negative because j hat usually points up, so we're flipping it actually. So we can write it out. We can write these vectors out like this. We can write a is equal to ax times I hat plus ay times j hat. Right? So ax times I hat plus ay times j hat, and then we can write b as bx times I hat plus by times j hat. And then if we wanted to add a plus b, and I'll show you this graphically as well, we just have to add these expressions. And combining like terms, right, if we factor out an I hat out of these two terms, we'd see that what we're doing is the x component is just the sum of the x components of the two vectors, right? So you can add components like this. Right? And to show this graphically, right? Well, if I have this ax and this bx, that looks like, well, I don't want to do that in that color. Um, that looks like ax plus bx would look, right? This would be our ax plus bx times I hat. And actually, sorry, I should have put it. So if I have this, I'll have this ax down here, ax plus bx, right? This length looks like it would be about ax plus bx. And now we know ay is a little bit bigger than, by is negative, and ay is more positive than by is negative. So it would be just a little bit up here. And this would be ay plus by times j hat. And we'd see that this, if you just added the vectors in the normal way, right, which is you would put this here, you would actually see a very similar vector, right? If it were a perfect drawing, they would be the same vector. But you see how this should in theory work. Okay, so I'm gonna erase this. Hopefully you got this. Actually, sorry, that's not the part I wanted to erase. I want to erase this part. So now I've got two last things that I would like to talk about. The first thing is a dot product. And a dot product is, probably the best way I can explain it, is the product of, it's sort of a measure of how similar vectors are in a way. Um, so I'll show you kind of what I mean by that. So I'm just going to redraw my vectors a and b, these same vectors, right? And I'm going to draw them kind of like this. So the dot product of so a dotted on b, right, is a way of multiplying vectors. And what we'll be doing, right, is if you see this, right, we have a component of a. There's a part of a that I'll show right here. This is a component of a, right? You see it's sort of perpendicular. Maybe I should have drawn it a little shorter. It's not supposed to be the same as b, but this component of a is parallel to b. And I'll call this literally a parallel, right? Well, a dotted on b is the component of a that is parallel to b times b, which is the same, right? We see b does have a component parallel to a down here, right? Sorry, no, not down there. Sorry. Um, so this is equal to a goes this way, right? So b, this is a component of b that's parallel to a. Hopefully you see that. This is a component of b and it's parallel to a, which is the same as a times, right? This is the magnitude of b, magnitude of the parallel component, is a times the component of b that is parallel to a. Right? I know this is a little bit hard to see, but hopefully you're just realizing you're just multiplying the vector by the component of the other vector that's parallel to it. And the other way you can do this, and if you don't understand it, go look in the dot product in Khan Academy. I'm just trying to go fast through this. Um, there's two other ways you can look at this. One is this is it happens to be, and you can kind of see this just if there's an angle between A and B, there's an angle theta here between A and B. All right. That's not easy to see. Over here, there is an angle theta. And the dot product is equal to A times B, the magnitude of A times the magnitude of B, times the cosine of theta. And so actually A and B, right, it's going to be at its maximum when they're parallel, because then cosine of theta, cosine of 0 is 1, right? If they're not parallel, it's going to be less than 1. If A and B are perpendicular, right? If A and B are perpendicular, and this is very important, if A and B are perpendicular, then the dot product between two perpendicular vectors is 0, right? Because there's no component of A that's parallel to B, no component of B that's parallel to A. The cosine, the angle, right, is 90 degrees, or in radians, that is pi over 2 radians, right? And the cosine of that is 0, right? So the dot product would be equal to 0. Now, if they're anti-parallel, if they're going in the opposite direction, their dot product will be their magnitudes multiplied, but their dot product will be negative because they're in the opposite direction, right? So that's why right, the closer two vectors are together and the longer they are, and the closer they are together in terms of like their angle, the higher their dot product will be. If they're pointing in the opposite direction, their dot product will be negative. If they're not pointed in the same direction, if they're perpendicular, their dot product will be 0. The other way we can calculate a dot product is by multiplying the similar components together, right? So this is the last thing we're going to do with dot products. Then we've got one last thing for this video. A dot B is, we're going to just multiply the AX times BX, right? And then add that to AY times BY. Or not plus BY, times BY. I think I said that, just I didn't write it. So AY times BY, right? All right, awesome. I'm going to erase this, hopefully you've got it down. Just one last thing for this video, and then we'll be done with the vectors. And again, just go on to Khan Academy if you have any questions in their vectors section. We can have a three-dimensional vector, right? Or four-dimensional, five-dimensional. We can have as many dimensions as we want. I'm going to do this in 3 dimensions, but then you'll see easily, I'll show you how we can sort of generalize it. So in 3 dimensions, we have a z, which z in this case would be going out of the screen, right? So it's hard to draw, and I can't draw 3 dimensions, so I'm not going to draw it. But we know that the vector is that a vector can be written vx times I hat plus vy times j hat plus vz, right, the component of the z direction, times k hat, which is the unit vector, and the k direction is just a vector of magnitude 1 coming out of the screen. We can use actually the 3-dimensional version of Pythagorean theorem. You can look that up if you're not familiar with it, or it's really the same as the 2-dimensional version. It's you'll see it's pretty easy to show. The magnitude of v squared. Now remember, Vx, Vy, and Vz are scalars. Scalars are quantities that are not vectors, right? So they're scalars, so I don't need to write magnitude squared. It's just, right, Vx squared, right? Because these are just scalars that you're multiplying by the unit vector to get a component. So the magnitude of v squared is Vx squared plus Vy squared plus Vz squared. Right? So the magnitude squared of a vector, right, is just the square of its of these coefficients for the components, right? And we can also, if we have two vectors a and b, which are ax times I hat plus ay times j hat plus az times k hat, etc., right? A dotted on b is just, and it's the same thing. If the vectors are perpendicular, the dot product's going to be, if the vectors are perpendicular, the dot product will be 0. If they're parallel, the dot product will just be the magnitude of their vectors. If they're anti-parallel, dot product will be negative, and otherwise the dot product will be somewhere in between. In all cases, and I'll show you this right after, so ax times bx plus ay times by, right, plus az times bz. Right? And if we added, if we imagined a four-dimensional world, we could just, right, this would just be plus v fourth component times the unit vector in the fourth direction, right? And then it would be plus, you would have, in this equation, you would have plus v fourth component squared. Here you'd have then a fourth component times b fourth component, right? And etc. on and on. In all cases, right, with the dot product, and this is so important, you'll want to write this down, right? We'll have perpendicular, the dot product is equal to 0. Parallel, the dot product equals a times b, the magnitude of a times the magnitude of b. Anti-parallel, that just means the same word, means the dot product will be negative a times b. In general, this is always true. This is going to be the very last thing for this video. In general, it is always true, and you can try to prove this or you can look up a proof, that the absolute value, this is not a magnitude because a dot b is a scalar. Its dot product is sometimes called the scalar product, right? But this is a magnitude, so if it's negative, it's just the positive version, right? A dot b always is going to be less than or equal to a times b. And if you think about our cosine theta rule, right, this would make sense because it's equal to a times b times cosine theta. Cosine theta is always less than or equal, or the magnitude of cosine theta, or the absolute value of cosine theta, is always less than or equal to 1, right? Meaning that to get this, you're multiplying this by either 1 or something less than 1, which would make this less than or equal to this, right? So that should make sense. This is important. And if you don't understand that explanation, look up, just look up properties of dot products. You'll see it on Khan Academy. So that's it. I will see you in the next video.